Okay, let's get started. So I really have only one announcement, which is the homework ones should be returned tomorrow. So the TA's gonna give them to me tomorrow before class, before my office hours, and then I'll bring them to class. Are there any questions? When I ask for questions, it's time for questions. Yes.
So I was going over like the lectures, and lecture 1 you said there was a 5 tuple, but you said the start state is the S is the start state, and then like F is a set of final states.
So you were talking about DFAs, I'm guessing. So with DFAs, we had this 5 tuple sigma delta Q0F, where Q0 is an element of a set, and F is a subset of Q.
So Q0 is always like one variable?
Is always a member of the set capital Q. So there's always a state in the DFA.
Okay.
Yep.
Well, that makes sense.
Yeah, so can a DFA ever have 0 states? No, why not?
Because Q0 is a blank.
Yeah, because Q0 is definitely an element of a set. Can anything be an element of the empty set? No, so the capital Q has to be non-empty. Can F be the empty set? The set of final states? Yeah, that's fine. Because there's no stipulation that the subset has to be non-empty. Okay, you had a Yeah, you wouldn't lose points for that. So the question was, if I asked you to draw an NFA and you draw a DFA, would you lose points? And the answer is no. You wouldn't lose any because all DFAs are NFAs. If I asked you to make a DFA and you wrote an NFA, would you lose points? Yes. Okay, so just be careful about that. The questions on the test, so it's already made, I just have to print it. The questions on the test are supposed to be very specific. So it says like, for example, construct a DFA for this language, or prove that this language is not regular, or are these two definitions equivalent? So like, here's one definition of something we learned, here's another definition, are they really the same thing? So it's really specific things. It's not like, show, like you have a language here, show that it's regular. So if I asked you like, okay, here's a language, show that it's regular, what could you do for it?
DFA.
Yeah, so you can do a DFA or what? NFA or do closure, yeah. But what things could you make? A regex or? There's a fourth one. It starts with a regular and ends with a grammar. Regular grammar, right? Because we showed that they're equivalent to NFAs. So with that type of question, it could be very open-ended. You can make any one of those 4. But every question in the test will be something like, construct a DFA for this, or construct an NFA for this, or a regex for this. Convert this regex into an NFA. Convert this NFA to a DFA. Convert this DFA to a regex. Things like that. So it's very specific things. Okay? Here's another thing that I'm sure some people will not listen to me, but I'm just going to tell you right up front, and it's going to be bolded in the test. So you shouldn't miss it. There's going to be some questions which are going to state something. So like, an example one, this will not be on the test. All finite languages are regular. Is that true? I got a no and a yes. Any maybes? Great. So what's the answer? Yes. Why is it yes? No, just because it's finite, that doesn't explain why it's true. So why is it true? Make an NFA for each of the strings individually, and then do an epsilon to all of the start states of each of the pieces. Why would this not work for infinite languages? I can just make a NFA for each of the strings individually, and then do epsilon to all of the strings. Why would this not work for infinite languages? I would have infinitely many states. Are we allowed to have infinitely many states? No. What letter in the three-letter acronym forbids that? The F. Okay. So, but going back to that, so all finite languages are regular. So those questions I'm going to have in the direction state to state the answer true or false and to explain your answer. And in bold, it's going to say all points are for the explanation. Okay? So you have to state true or false, but you have to explain your answer. If you just say true or false, how many points are you going to get? 0. Okay? So don't be surprised. Don't have your surprise Pikachu face when you just write true or just false or leave it blank and you get 0 on that question. Okay? So if write out the explanation for why it's true, or if it's false, what should you show to show that it's false? So like if I said, all infinite languages are regular. Yeah, find one counterexample, one exception. So what would be a counterexample to all infinite languages are regular? Yeah, no, an infinite language that isn't regular. That would be a counterexample. What would be a counterexample to that one? Yeah, so that would be an example. So 0 to the n, 1 to the n, and at least 0. Yeah, so another one we did was, I won't write it all out, but equal number of zeros and ones. So that's actually the first one that we did. And there are others that you can think of too. So whenever the question is actually false, write false and just write the counterexample. Don't write a whole long paragraph explaining, telling me what a non-regular language is or what an infinite language is. I know what it is. Okay, I'm teaching the class. I know what that is. Just state the counterexample and you're done. Okay, so I'm not expecting long answers to these questions. Even though they may have a lot of space, they're not meant to be long questions. Okay, there's not a lot of writing, and I've done the test myself. They're not meant to be long. Okay, just be short and concise, but be clear of what you're actually saying. Does that make sense? Any other questions about the test? Yeah.
So we haven't practiced later part of the chapter 1. So
What part?
like the regex, the conversion of GNFA, that there are no questions on homework 2.
We did an example of conversion though. We did a conversion, GNFA conversion though.
Will you be posting homework 3 before the exam?
Oh, you mean for homeworks? Yeah, I can post a homework 3 tomorrow. Yes, but is there a GNFA conversion on homework 2? I don't remember. There may be. I'm not sure. I'll check in the break if I remember. But if there isn't, I'll make a homework 3 by tomorrow.
And also for pumping them on.
Yeah, but there are pumping lemma questions on homework 2. I know that for sure. Other questions? Yeah.
So the exam's up to where you're going to teach.
Yeah. So everything on regular languages. Mhm. If it has the word regular associated with it, it's probably going to be on the test. If it doesn't have the word regular with it, it probably isn't. Okay? Other questions about the test or homework 2 or anything? I see that Piazza is rather inactive lately. So what do you think I recommend you do? Post. Anyone have any doubts on the material at all? You're not 100% clear on material. Just raise your hand if you're not 100% clear on material. Who do you think I recommend should post on Piazza to resolve these doubts? Yeah, anyone who raised their hand, okay? So any questions in general that you want to resolve now? If there are no questions, you see why I'm asking these things, right? Okay, so I'm not living in a vacuum. Okay, so what did we talk about at the end of last Thursday? What's that?
Grammar.
Yeah, grammars in general, yeah. Right, so we start, what type of grammar did we start with? The first type of grammar. Yeah, regular grammar, right? So we started with regular grammars. And what did we show about regular grammars? What's that? It's a four tuple, yeah. But what about the languages they recognize? They're the same as NFA, which is what called? What are they called? The regular languages. Yeah. So the regular grammars recognize the regular languages. Okay. So did we show that some languages weren't regular?
Yes.
Yeah. So, and what was the tool that we used for that? Pumping lemma. Right. So what type of grammar did we start talking about because we found languages to not be regular? We graduated from regular grammars to what type of grammar? Context-free grammar. Right. So what was the difference between these? You don't have to be technical. So what's the a high-level description of what the difference between these two is? So regular grammars were restrictive in what way?
Regular languages.
Well, yeah, but
You can have.
don't answer that way on the test. Yeah, go ahead.
Like you can have variable and like.
Right, yeah, but a high-level description. So what changed? What was the parts that changed? Regular grammars restricted what types of things? It's a 5-letter word. Starts with R. Next letter is U. Next letter is L. Rules. Okay? So regular grammars restricted the types of rules that you can have. And what was pointed out was the right side of the rules could either be epsilon, a single terminal, single character, or just a single variable and nothing else, or one terminal and one variable and nothing else. That seems rather restrictive. And what was a small change that we can make to immediately get a non-regular language? Well, what we did was, instead of just having one terminal then one variable, what if I instead also allowed you to have the variable then the terminal and the other way around? So we have 5 types of rules instead. Well, then we can make a language like this. Let's see, S1 or empty. And we analyzed this grammar last time. So this is not a regular grammar. Why? Yeah. So one rule has the terminal first, and the other rule has the terminal after. So it's not a regular grammar, but barely not a regular grammar. But what language is this? Is it regular or not? It is not, because if I generate a 0, then I must at some point, if I'm going to get a string at some point, I need to generate a 1 at the end. So I'm going to generate a 0 over here and a 1 over here, and then I'm going to work my way in. So I'm going to have a string which has the same number of 0s and 1s in it. And we know that that's not regular. But if we just keep adding, you can have a rule of this type. If you can have a rule of this type. You can have a rule of this type. Do you think that's going to be any fun? Well, is any of this material fun? No, I'm kidding. But that could be quite cumbersome. If I just tell you 100 types of rules that you're allowed to have, what if I just said, put anything you want on the right side? That could be a lot easier to analyze. And clearly it gets at least the regular languages because every regular language has anything on the right side already. So we immediately get the regular languages, and by this, we get more. And then now we just want to know how much more do we actually get. So a context-free grammar, CFG, looks like an airport name, is like a regular grammar, but the rules, so I'm going to be more formal than how I was last time, but the rules are of the form, instead of having variable goes to something, variable goes to something, we're just going to have one type of rule, which says a single variable can go to anything. So where by anything I mean x is an element of the variables or the terminals in any order in as many as we want. So by putting star here, I'm saying the right-hand side of this rule can be as long as you want or as short as you want. And you can pick from the variables or the terminals in any order as many as you want of those. So every regular grammar is like this because the right-hand side is you just pick either epsilon, which is an element of something star, a single terminal, which is just picking one thing which is from the set of terminals, a single variable, just pick from V, or I can pick from terminal, then variable, which is the first time through picking from sigma, and then the second time through picking from the variables. So here we really do get all the regular languages. So then a context-free language, or a CFL, is one that is generated by a CFG. Generated by a CFG. So if you give me a context-free grammar, any one at all, that is a context-free language. We're going to define it to be that way. Just like how regular language corresponds to the language of a DFA, a context-free language is for a context-free grammar. So it's just a definition here. So what can you tell me then about the language which is of this grammar above, which is 0 to the n, 1 to the n, and at least 0? What can you tell me about that language?
It's a context-free language.
It's context-free language. What is it also not? Not regular. So we have an example of where context-free languages are properly a superset of regular languages. They have every regular language inside them, but they have more languages than that. And this is one of the examples. Okay, any questions about that? Okay, so we talked about derivation before, which is just a sequence of applications of rules and eventually getting to a string full of terminals. If it has a variable somewhere on the inside, so some variable with whatever on the left and right, then that is not a full derivation. So if we start with the start variable and we apply a bunch of rules to get this string, this is not a full derivation yet. But if we keep going and apply more rules, so maybe we replace this variable a with other stuff, and then we get a string w1 up to wn, and then I'll just note here that they're all terminals, then that is a full derivation. So derivation, you start with the start variable, you work your way through, and then you get a string of just terminals at the end. Because for a context-free grammar, we always have a single variable on the left side. So we can never replace terminals at any point, okay? Any questions about that? Anyone do the example I mentioned at the end of last time? Oh, yeah, go ahead.
I forgot. Is it the context-free grammars that have an NFA, or is it just the regular grammar?
So, a good question. So, does every regular grammar have an NFA associated with it? Having the same language, yeah. So, we can convert a regular grammar into, I'll do it this way, into an NFA, and I can convert the other way. So this is what we talked about, I forget which day, but we talked about it before. Remember that every regular grammar is already a context-free grammar. So the grammars that we talked about don't have to have arbitrary things on the right-hand side. We can restrict it if we want to. But it's just I'm allowing you to put whatever on the right side. It's the same idea as a DFA and an NFA. Every DFA is an NFA, but not necessarily the other way. Same idea here. So every regular grammar is already a CFG, but it's not true, and so I'll put this in red. It's not true that it's you can convert from a CFG back into a regular grammar, because if we could, then we can convert the grammar for 0 to the n, 1 to the n, back into a regular grammar, but we know that there doesn't exist one. So that we can't necessarily convert back. Okay, does that answer? Cool. Other questions? So what was the example I mentioned for you to work on over the weekend? What's there?
Can you give 2 examples?
At least one. I'm thinking of one. What was the example I mentioned? Hint.
O n to the cube.
What's there?
0 n to the cube.
0 n to the q.
To the n to the cube.
Oh, okay. So it was like this, you mean? And what are the qualifications on n and q? Okay. Yeah. So I'm gonna actually modify your example just a bit, and I'm gonna call this thing L sub q. So I'm gonna parameterize it on q. So the one that we did in class was L2, and so this was in class, and we showed that to not be regular. And I asked you to work on L3, L4, etc., and all of them are not regular for almost the same reason. But I want to do the example I mentioned on context-free grammars. So what was the one I mentioned? So the motivation was when you compile your programs, let's just say you're writing C++ or Java or whatever, and you compile a program and you see one error, which corresponds to you didn't have enough closing curly braces. You fix the error, and now you have 100 errors. Anyone encounter that? Yeah. Anyone know why that occurs? So what the compiler does is, so this is the second time I'm mentioning it. So what the compiler does is it goes through your program, ignores everything but the curly brackets, the parentheses, and the square brackets, and it matches them up. So let's just say, for example, that we're only dealing with curly brackets. We don't have parentheses or square brackets, just for simplicity. So maybe I'm going to feed you a string, and I want you to tell me whether or not it's balanced or not. So an example could be, here's a balanced string, because for the outer left curly bracket, the closing one is over here. For the next one, it matches here. And for the middle one, they match here. And there's nothing in the middle, so therefore these are matching. What if I instead put another curly bracket here on the end. Is this a matching set of curly brackets? No, because there's nothing that's going to match the green one. However, consider this. Could it be possible in a long string like this, not necessarily just this piece right here, could it be that this curly bracket right here matches up with this one? Yeah, so it could be that it's not going to be so simple like this. So for example, it could be that we have this string. So I'm going to actually make this clearer. Instead of having these left and rights, I'm just going to call them L and R, because it is easier to read that way. So we're wondering if this is a matching set of L's and R's, left curlies and right curlies. Well, it could be that this L on the end could match with this R on the end, right? Because an L has to match with an R somewhere. But we know that that's not the right R, right? So which one should it match with? The next one in, right? So it should match with this one. So can we make a context-free grammar for this? Well, let's see what happens. Well, what about the empty string? Is the empty string a set of balanced parentheses, curly brackets, L's and R's? Yeah. So, namely 0 of them, so that's fine. But let's see. Well, let's just say we do have a matching set of balanced parentheses, okay, curly brackets. Well, let's see. If we have a matching set of balanced L's and R's, then let's see. If we have a curly bracket right here, I guess I'm going to go back to them. It's easier to visualize, I guess. And then there could be some stuff in the middle, but at some point, what should I see eventually? The other one, the right curly bracket. Well, let's see. By the example on the upper right here, is this enough to describe balanced curly brackets? No. What could appear afterward? What can appear over here? Maybe I shouldn't do that. What can appear over here? Another set of balanced curly brackets. Well, let's see. Let's put our Mat 243 hats on. By induction, could we assume something about the variable s here? Could we assume by induction that s generates the smaller balanced curly brackets? Well, if we assume that, then let's add another rule. S could either generate epsilon, or it can generate a left curly bracket with something in the middle, which is a balanced set of curly brackets, which we assume to be S. So by going down into this rule, S will assume can generate the strings that are balanced. So if we drill down deeper, then on the inside there must be a set of balanced curly brackets. Well, by that reasoning, the stuff that must appear afterward must also be S. But this actually gets us balanced parentheses. And you can actually prove that this really does work. So for any set of balanced parentheses, then you should be able to express it either as the empty string or as a left curly bracket with a balanced set of curly brackets on the inside, followed by a right one somewhere, and then another set of balanced right after it. Okay? Any questions about that? So let's actually generate the string above here. Well, let's see. How can we generate the LLRRLR string? Well, what rule should I apply first? The second one. Should I apply the first one? I could, but will I get the string I want? No. So I apply the first rule, and I get this. Okay. With regular grammars, did we have any choice of what variable to use at a certain point? With regular grammars?
No.
No, why not?
There was only one.
There was only one variable at every point. So we only had one variable to pick from. How many do we have here? 2. Which one should I use? The first one. Okay, so let's take your suggestion and let's do the first one. So the first S we're going to replace. So which rule of S should we apply to the first S in this derivation? The first one or the second one? Second one, because we need the L and R on the inside. So then we can get the left, and then we just replace it with what the rule says, which is this. In fact, I'm going to change this to another color so that you can see it better. So this is left, S, right, with an S there. So this is just applying the rule, the second rule, to the inside S here. Well, we have 3 variables now. We went from 2 to 3. What should we do now? We can eliminate this first one by applying which rule? The first one or the second one? First one, yeah. To replace it with epsilon. So this is the first S, I should say. First S. And then we're going to get this. The other 2 S's are still there because I can only replace one variable at a time. What should we do next? Yeah, we can do epsilon for the second one again. So then left, right with an S on the end. And then now what? So this is first S again. Well, there's only one variable, so we're all fine there. Which rule should I apply? The first one or the second one? Second one, good. So then we have left, right, and then left, S, right, S. And what's going to eventually happen to these 2? Yeah, epsilon for both. So I'm just going to simplify it so we don't have to do that tedious work again. Okay? Any questions on how we actually did that? But note, thank you, Discover. But notice here, did we have a choice of what variable to pick? Yeah. We didn't really have a choice of which rule to pick because at every point, we're still going to get the same string, although that's not technically true. But we have multiple S's to deal with, right? So for like the first instance, I could have either picked the first one or I could have picked the second one. If I pick the second one, could I still end up at the same string at the very end?
Yes.
Yeah, it's just doing the rules in the opposite order. Why does that always work? So if I have an arbitrary CFG, and I have a derivation so far with a variable here, variable here, variable here, variable here, and let's just say I pick the third one instead of just the first one, will I always get the target string if I apply the rules in the right way? Yeah. Why? What type of grammar is this? Context-free. Do you think that context-free came out of nowhere? What does context-free mean? It means replace a variable with stuff, whatever the thing is on the right side of the rule. Well, did we pay any attention at any point when we applied a rule here to what was other than that variable itself? Did we pay attention to anything else in the derivation other than that one variable? No. So if I looked at this first variable right here that we replaced in our derivation, the one we did I care about the left, the right, and the S afterward? Did that affect which rule I picked? No, it didn't affect anything. So, in fact, because it's a context-free grammar, we're free to pick any variable we want and replace it right then and there. I don't have to go in a certain order if I don't want to. But it'll actually be more convenient to think about things instead of just picking arbitrary variables to fix. Let's just fix the first one. So that's actually what we did here. We looked at the derivation we did, and we looked for the first variable that appears leftmost in the derivation. So what kind of derivation do you think this is called? We picked the leftmost variable. What do you think it's called? Leftmost derivation. So a leftmost derivation is one that always replaces the leftmost variable. If there's no leftmost variable, then we're done because we have a string full of terminals anyway. Otherwise, there's a variable and there is a leftmost one for that reason. Okay? Any questions on what a leftmost derivation is? So we're not going to actually talk about this yet, but I want you to keep it in mind. So think of a leftmost derivation. So first off, before I say that, if we have any derivation at all, can we get a leftmost derivation for it?
Yes.
Yeah. It's just we rearrange which of rule applications that we did because we're just replacing variables. If I have a leftmost derivation, can I get a normal derivation? Well, it already is one. So we always can get a leftmost derivation. But think about this. Because we're picking the leftmost derivation, what appears to the left of that variable, the leftmost variable? What appears to the left of it? Terminals only. So by that reasoning, we're kind of progressing through the string forward. We're never going backward. So for that reason, we can actually think about this from a machine point of view. Think of a DFA or NFA. It only moves through the string left to right. And that's kind of what we're doing right here. We're moving left to right. And this is actually how we will get a machine model for context-free languages, okay? So we're not going to actually talk about that. I want you just to keep it in mind. Any questions on derivations and leftmost derivations? Okay, so let's see. For your compiler, let's just say it's doing this analysis of your program, that is looking at curly brackets and then figuring out whether everything's okay. Do you think it's storing it as a derivation like this? No, so this is not actually what it stores it as. Does anyone know what the compiler actually stores when it's actually computing all of this? What's that?
The count?
It could do count, yeah. So it could do count. If we're only dealing with curly brackets. So if it's just left and right curly brackets, then yeah, we can. But the problem is if we have arbitrary numbers of characters, so if it's not just left curly bracket, left parentheses, left square bracket, but we also have other stuff, we could have a count associated with each one of them, but the problem is we can't really do that if there are other characters. For example, so if we wanted to augment our grammar with curly brackets and parentheses, if we just did a count, then what about this string? The count would be okay because if we add one for every left guy and subtract one for every right one, then the count for both of these is 0, but it's clearly not balanced. So let's see. We need an alternate structure here. So has anyone ever heard of a parse tree? Yeah. So a parse tree, which is what we're going to do next, is an alternate way of expressing leftmost derivations. And the reason that we're going to do that is it leads to other stuff that we're going to get to eventually. So a parse tree is a tree where, so this isn't really a formal definition, but so we'll do an example that will highlight this. So it's a tree where the root is the start variable. All the leaves are either from the set of terminals or, I should do it in English, or are epsilon. And every non-leaf node's children are a result, so I'm making this up on the spot, I'm completely serious, are a result of a rule application corresponding to that variable. I'll do an example, I promise. So the idea here is we're modeling how the derivation actually works in a graphical way. So the top of the tree, so computer scientists love to think of trees as growing downwards, but the root at the top is the start variable. And then going down the tree, we're looking at rule applications. So with the start variable at the top, the nodes right beneath the root node are a result of applying a rule from the start variable to those things. And if we generated a variable at that point, that node will generate something else. And if you just read the leaves, the things at the very bottom of the tree all the way through, those are all terminals or are the empty string. So let's do an example of, say, this derivation right here. So the string we want to look at is the left, left, right, right, left, and right. Okay, well, what we did in the grammar is we started with the start variable. So at the top is the start variable. And we immediately applied the second rule, actually, which is to get a left curly bracket with a variable s. I should move it over here. The right, I can't talk. The right curly bracket, and then another instance of s over here. So every leaf node in this tree, so the things at the bottom are terminals. Well, we have two leaves right now that are variables, the instances of s. So the first instance of s corresponds to another application of that second rule again. So if we have a left, we have an s here again, right, and then another s. Actually, I'm going to move this. It's going to get bigger than I thought it would be. Okay. And then on the inside, we made this s in the center go to epsilon because we applied the first rule there. We made the second s over here go to epsilon. And then we made the final s on the far right have another rule application, which was the left. This is not as readable as I thought it would be. Right, and then s, and then both of these went to epsilon. It looks like a bunch of seahorses. I'm going to actually fix this because it's not as readable. I'm going to replace it with L's and R's. but it'll do the exact same thing. Well, not exactly the same, but analogous. So this is a parse tree. And how do we know what rules were applied? Well, we look at the top, we go down, and we know, oh, that rule was applied. And then if we look at an S in the middle, we look at its children, we know what rule was applied. If it was S goes to epsilon, then the first rule was applied, otherwise it was the second one. Okay?
We have to draw this.
What, sorry?
We get to draw this.
Yeah, you may get to draw them, but we're not going to really focus on these. It'll just turn out to be a useful concept to look at, but we're not going to actually draw these. Because as you can see, it can be quite unwieldy if for any larger grammar or larger string. Okay, let's see. Any questions about that? Yeah.
Wait, so why does the start keep going down at the start, like keep having the S down?
So yeah, so the start variable's at the top, but any arbitrary other variable could be a non-leaf node in the middle. It's just that there was only one variable in our grammar, so it's always S here. It's just the start variable has to be at the top. So it's modeling the derivation from the start, which is at the top, all the way down. Well, let's see. So I'm going to actually propose to you another grammar for this same language, the balanced parentheses one. So let's consider this language. And there's a reason why I'm going to propose this. So let's look at this one. So if we have, so we always got to get the empty string. So that's always got to be there. Well, consider this instead. Suppose that I have a balanced set of parentheses right here. And could I have another set of balanced parentheses associated right next to it? Yeah, because no matter what happens, either it's a single set of balanced curly brackets or is at least two of them. Well, what if it's exactly one? So that means that the start of the string must be left, the end of the string must be right, there's nothing afterward, and everything else is between those two. So what could happen is we have S with left and right immediately after, and we don't put the S on the right side, okay? Or it could be two sets of parentheses, okay? So here's a set, here's another set, and they're right next to each other. Well, what if you have three sets? Could it be that it's just two with, and then I apply a rule on the second one to get the other two? What we can express this as is S with S. So if S generates the set of balanced curly brackets, then I can set it as one set followed by another set. Okay? Well, every set of balanced curly brackets is either exactly one or at least two. Well, if it's at least two, I just apply this rule over and over and over again until I get the number that I need. Okay? So this is an alternate grammar for the language. Let's see. Do we want our compilers to be deterministic? So if I compile the program, it'll always say the same answer. Furthermore, do we want the compiler to say it compiles or doesn't in the same way every time? So if I give it the same program, should it do the exact same amount of work every single time? Yeah, well, consider this. Well, what are the ways we can generate the empty string in this grammar, the second one I gave you? Well, what is the easy way out to get the empty string? The first one, yeah. So one way is I can have S generate empty directly. What's another way? Well, I better not apply the second one because that generates some characters. So I better apply the third one. Well, then I can just make the first S disappear, which I'll get S. Then I'll get SS, and then I'll get SSS, and then you see the pattern. And then eventually I'm going to get empty at the end. How many ways can I make the empty string in this grammar? Infinitely many. What is true? So could this possibly happen with another string, so a non-empty string? Yeah, think of the same idea. Do the left S right guy, and then with the middle S, replace it with SS, and then make both those S's disappear. So in fact, there are many ways we can make every string in this grammar. Isn't that kind of annoying? What do you think is true about this other grammar that we did? What do you think is true here? Turns out every single string can be generated in exactly one way. Well, think about the second grammar, the generation of this through not just a derivation point of view, but a through a parse tree point of view. So the first one, so this is for 1, we had S immediately generate empty, whereas the second one had S make 2 S's, and let's just say we are going to try to make these S's go away immediately. And those S's make empty. So this one is for 2. What is different about these? Sorry. What can you say about these 2 parse trees? They're different. Well, does it actually matter which rule application I actually did to get a difference between these 2? No, there's actually a fundamental difference between these 2. What about this one? For the same string. Is there a different parse tree for this string? Well, here's the thing. Is there a different parse tree with a leftmost derivation for this string? No. Okay, so we'll talk more about that after the break.